Chapter 24, Probability and Statistics. Section 24.1, Basic Probability Theory. There are two types of probability distributions: discrete probability distribution versus continuous probability distribution. In a discrete probability distribution, the number of possible events or outcomes is countable. We can count individual outcomes. In a continuous probability distribution, the number of possible events is uncountable. The discrete probability distribution can be illustrated with a bar chart. We cannot do that for a continuous probability distribution. Here are some discrete examples, like throwing a die, drawing a card, or tossing a coin. When we throw a die, there are 6 possible outcomes from 1 to 6. When we draw a card from a deck, there are 52 possible outcomes, excluding the jokers. When we toss a quarter, there are 2 possible outcomes, heads or tails. Now let's throw 2 dice. There are 11 possible outcomes from 2 to 12. Well, to get a total value of 2, the probability is really small. It's only 1 over 36. Roughly 3%, because we need both dice to be 1. Therefore, it's 1 over 6 times 1 over 6. The probability of getting a 12 is larger. It's not even larger. It's also 1 over 6 times 1 over 6. It's 1 over 36. Only because to get a 12, you need both dice to be 6. Alright, therefore you have a very small probability over here, 1 over 36. What's the probability of getting a 3? Well, it's different, because this time when we threw 2 dice, it can be 1 and 2, or it can be 2 and 1. So the probability is 2 times 1 over 6 times 1 over 6. It's 2 over 36, a bit larger. What's the probability of getting a 4? Well, you could get 1 and 3, 2 and 2, and 3 and 1 out of this 2 dice. So the probability is 3 times 1 over 6 over 1 over 6. It's going to be 3 over 36. The probability reaches the maximum if the sum is 7, because to get a 7, you have many different ways. You can have 1 and a 6, you get 7. 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, you get 7. So the probability of getting 7 is 6 over 36. We have 6 different ways. What about the probability of getting 8, 9, 10, or 11? Well, the probability starts to decrease. It's 5, 4, 3, or 2 over 36. And when we sum up all those probabilities of all possible outcomes, it should be 1. You can verify this. This is the probability of getting a value of 2 from 2 dice. 3, 4, 5, 6, 7 maximum. Alright, and then 8, 9, 10, 11, 12. If you sum it up, you get 1. Now let's look at the expectation value of throwing just 1 die. It's 3.5, because you may get 1 or 2 or 3 or 4 or 5 or 6. You take the average, 3.5. What if you threw 10 dice? The sum is going to be 35 plus minus some deviation. The average is going to be 35 when you threw 10 dice. If you threw 10 dice 1 billion times, alright, and then look at the distribution, you'll see the probability is maximized at 35. That's the expectation value of throwing 10 dice. Now let's look at some poker cards. When we draw 1 card out of a deck, the probability of getting an ace is 4 out of 52, because we have 4 different aces. We have ace of diamonds, ace of hearts, ace of clubs, ace of spades. So when you draw 1 card out, well, there are 52 outcomes. Out of this 52 outcomes, 4 are desired outcomes. Now let's draw 2 cards. What's the probability of getting an ace and a king? Well, it's more complicated. First, we draw 2 cards. What's the total number of possible outcomes? Well, it's 52 times 51 over 2 factorial. Why that? The first card you have 52 different options. Second card, only 51 options left. So it's got to be 52 times 51, right? But then you need to divide that by 2 factorial, because if you get 2 cards, if you get A and then B versus B and then A, we consider this 2 the same outcome. We count A and B or B and A as one single outcome. So we need to divide that by 2. More accurately, we need to divide that by 2 factorial, because when you have 3 cards, you can have 3 factorial different orders. So you can have ABC, ACB, BAC, BCA, CAB, CBA, 6 possible different orders. But we count them as one possible outcome. So we need to divide those by 3 factorial. So get back to this. What's the opportunity of getting 1 ace and 1 king? So when we draw 2 cards, there are many possible outcomes. Over here it's 52 times 51 or 2 factorial. Alright, this many possible outcomes. 16 are desired outcomes, because we can have one card being one of the 4 aces, and another card one out of 4 different kings. So 16 different desired outcomes. So you can have A of diamonds plus king of diamonds, A of diamonds and king of hearts, A of diamonds, king of clubs, A of diamonds, king of spades. And then A of hearts, king of diamonds, A of hearts, king of hearts, A of hearts, king of clubs, A of hearts, king of spades. So you can just get 16 different outcomes that correspond to 1 ace and 1 king. What's the probability of getting 2 aces? Well, that's going to be smaller, because again, this is the total number of outcomes of drawing 2 cards. And now let's look at the number of outcomes with 2 aces. There are only 6, because you can get A of diamonds plus hearts, A of diamonds plus clubs, A of diamonds and spades, A of hearts and clubs, A of hearts and spades, A of clubs and spades. So only 6. Only 6. Alright, why? Because there are 4 suites. The first one you have 4 options, the second one you have only 3 options left. And we're looking at only the combinations. We don't care about the orders, so we need to divide this 2 factorial different orders. We have only 6 outcomes. Now when we draw 2 cards, what's the probability of getting 2 cards of the same rank? It's only 3 out of 51, just because whatever the first card is, out of the remaining 51 cards, only 3 have the same rank, so it's 1 over 17. Alright, so we just do 3 divided by 51 is 1 over 17. There's another way to calculate this. Over here on the bottom, that's the total number of outcomes of drawing 2 cards. Alright, 52 times 51 over 2 factorial. Now, the possible outcomes. Alright, 2 cards of the same rank, how many are there? There are 13 ranks, so we have 13 times over here. Within the same rank, the first card you have 4 options, second card 3 options only, and then divided by 2 factorial, and then you do this calculation, you'll get the same number, 1 over 17. Alright, now let's draw 2 cards again. The probability of getting 2 cards of different ranks is 16 out of 17. Why is that? Whatever the first card is, out of the remaining 51 cards, there are only 48 cards with a different rank, right? So it's going to be 48 over 51. It's 16 over 17. Also, you can just look at this 2 paragraphs. Here, 2 cards of the same rank. Here, 2 cards of different ranks. Well, they complement each other. So the probability of getting 2 cards of the same rank versus the 2 cards of different ranks, if you sum them up, it should be 100%. So 1 minus 1 over 17, you get 16 over 17. When drawing 3 cards, the probability of getting all 3 cards of the same rank is this. Alright, this is the total number of possible outcomes of 3 cards. 52 times 51 times 50 over 3 factorial, because we have 3 factorial different orders, or so-called permutations. On top, you have 13 ranks. Out of each rank, the first card 4 options, the second card 3 options, 2 options over 3 factorial. And also you can just see, if you choose 3 cards out of 4 cards, there are only 4 options. It's just the you have another way of thinking about this. You need to pick a card and do not choose it. Alright, so 4 options as well. So 13 times 4 here divided by the total number of outcomes. That's pretty small. It's 1 out of 425. Now what if you draw 4 cards? Alright, you draw 4 cards. And the probability of getting all 4 cards of the same rank is even much smaller. Alright, because you have only 13 desired outcomes. You get 4 2s, 4 3s, 4 4s, 4 5s, all the way to 4 aces. On the bottom, you have this many different outcomes. You do the calculation. It's 1 out of 20,000. You can try this. You can try this all day and see how many times you get 4 cards of the same rank. Very slim chances. In general, the total number of possible outcomes of drawing m cards out of n cards is this. Okay, n factorial over m factorial over n minus m factorial. If the order of drawing those cards does not matter, we're going to count all these 6 different orders as one combination. Alright, so ABC is equivalent to ACB, equivalent to BAC, right? So when you play like blackjack in a casino, whether you get a ace and then a king, or a king and then an ace, I mean, that's just the same. But what if you draw m cards out of n cards, and what if the order matters? Well, if the order matters, then there are m factorial permutations. Alright, if you have m cards. So if you have 3 cards, you have 6 permutations, or 6 different orders. When you have 4 cards, you have 4 factorial permutations, or 4 factorial different orders. Alright, when you have 4 cards, or just let's say 4 objects, A, B, C, D. So you can have A, B, C, D, you can have A, B, D, C, A, C, B, D, A, C, D, B, A, C, B, D, A, C, D, B, A. I think I lost track. But in total, you will have 4 times 3 times 2 times 1, a total of 24 different permutations. Okay, so when you have A in the front, you have 6 permutations. When you have B in the front, you have 6 permutations. When you have C in the front, you have 6 permutations. When you have D in the front, you have 6 permutations. So in total, you have 4 times 6, 24 permutations. What if you have 5 different objects, A, B, C, D, E? And then you can have either A or B or C or D or E in the front. So you have 5 options. Alright? And for each such option, you have 4 factorial different permutations. So if you have 5 objects, you have 5 times 4 factorial permutations. 5 times 4 factorial is 5 factorial. So you have 5 objects, 5 permutations, 10 objects, 10 permutations. Alright? Alright, so the number of permutations can be much larger than the number of combinations. How much larger? Well, it's just m factorial larger. Alright, so if you see this expression and this expression, they differ by a factor of m factorial. Now let's look at some numerical example. Problem 24.1. Calculate the number of combinations of drawing 6 cards out of 10 cards. Calculate the number of permutations. So I'm going to just use these 2 equations. Number of combinations 10 factorial over 6 factorial over 4 factorial 200. 10. Number of permutations. Wow, this is going to be larger because for every single combination there are 720 permutations. 6 times 5 times 4 times 3 times 2 times 1, that's 720. So these two numbers differ by 720. 210 times 720, you get a number greater than 150,000. Such a large number of permutations when you just draw 6 cards out of 10. What if you draw 6 cards out of 10 cards? Alright, drawing 10 cards out of 10 cards. Alright, you have only one combination, right? It's going to be 10 factorial over 10 factorial over 0 factorial. 0 factorial is 1, and you get just one combination. The number of permutations, a lot. It's going to be 10 factorial. Alright, 10 factorial is this 6 factorial times 7 times 8 times 9 times 10. It's a huge number. Now let's toss coins. When we toss 2 coins, there are 3 possible outcomes. 2 heads, 1 heads, 0 heads. In terms of the number of heads, if we don't care, which coin is heads, which coin is tails. So when we see this 1 heads, actually you may ask, if you have 2 coins, which coin is heads, which coin is tails? Well, if the 2 coins are somehow like quantum coins, indistinguishable quantum coins, and then you have only 3 outcomes. But if you have real coins, like real quarters, right? If you threw 2 quarters, you know which is which, and you get 4 different outcomes. You get heads heads, heads tails, tails heads, tails tails. All right. And the probability is it depends. It's 25% here, 25% here, 25% here, and 25% here. But if my question is about the probability of getting 2 heads, 1 head, 0 heads, it's just 25, 50, and 25%. Now, what if we rig the coins? And to make them with 60% chance of heads, 40% of tails, just to make money illegally, and then we can calculate the probability differently. So let's say we have n coins. We toss n coins, and let's calculate the probability of getting I heads. There's an equation over here. The equation is this. It's going to be n factorial over I factorial over minus I factorial. So when you look at this, you probably realize this is the number of combinations of selecting I cards out of n cards. Now we're just selecting I coins from n coins. Alright, after you make the selection, all this I coins should be heads, and that's the corresponding probability. The remaining n minus I coins should be tails, and over here that's the probability of all these coins with tails. So that's why we have this formula, and we plug in numbers. Alright, so what if we are again tossing 2 coins? The probability of getting 2 heads, we plug in 2 here, 2 heads, we plug in 2 here, and then 2 minus 2, 0.6 to the power of 2, and this is 0.4 to the power of 2 minus 2, so all this done, 0.36. 0 heads, 0.16. In the middle, 0.48. You just do this. Well, we can verify this really easily. You have 2 coins, right? Both are heads. Should it be 0.6 times 0.6? 0.36. What's the opportunity of getting 2 tails? Well, 0.4 times 0.4 over here. What's the probability of getting 1 heads? Well, it's just 1 minus this minus this. You get 0.48. So we can easily verify this. But why don't we just do 60% times 60% here? Instead, we did this. I just want to show you a systematic way of computing the probability with rigged coins. What if we have 10 coins and we need to calculate the probability of getting like 6 heads out of 10 coins. And then you need to use the formula. It's going to be 10 factorial over 6 factorial over 4 factorial times 0.6 to the power of 6 times 0.4 to the power of 4. And then you can get a number at least. 2 coins is really simple, but when you get 10 coins, and we need 6 heads out of 10 coins, you need to use this equation. When we toss 3 coins, there are 8 possible outcomes. If the coins are distinguishable, if you have real quarters, you know which is which. There are 8 possible outcomes. But if those are quantum coins, like electrons, they are indistinguishable. There are only 4 possible outcomes. 0 heads, 1 heads, 2 heads, 3 heads. That's it. 4 possible outcomes. When we toss n distinguishable coins, there are 2 to the power of n possible outcomes. But if those coins are indistinguishable, we have only n plus 1 possible outcomes. From 0 heads all the way to n heads, there are just n plus 1 different possible numbers of heads. What if we toss 1 mole coins? Well, we get many outcomes. It's 2 to the power of 1 mole possible outcomes. What if all those 1 mole coins are indistinguishable? Then we have just 1 mole plus 1 possible outcomes, because we can have 0 heads, 1 heads, 2 heads, all the way to 1 mole heads. Again, there are 2 different types of probability distribution: discrete versus continuous. Now let's talk about continuous probability distribution. Yeah, continuous probability distribution, the number of possible events or the number of possible outcomes is uncountable. And also, between any 2 outcomes, there are an infinite number of outcomes, different outcomes between just any 2. Here, let's look at one example. If I know a particle is between 0 meters and 1 meters, right? And there are many outcomes, actually an infinite number of outcomes, right? You can have the particle at 0 meter, you can have the particle at 1 picometer. Between 0 meter and 1 picometer, you still have an infinite number of outcomes, right? You can have like 1 femtometer, 2 femtometers, and even between 1 femtometer and 2 femtometers, you can have like 1.1 femtometer, 1.2 femtometers, right? So you have an infinite number of outcomes between just any 2 different outcomes. That's continuous. So that's why we cannot simply display the continuous probability distribution with a bar chart. We have to use the probability density curve, all right, something like this. And the horizontal axis is just the possible outcomes, and we have a continuous distribution of possible outcomes. The vertical axis is the probability density. Here are 2 examples. One example is from quantum chemistry. The probability density of finding the electron at radius r in the hydrogen atom is this. Alright, it's the squared modulus of the wave function times r squared. The probability from r to r plus dr is the density times dr times the range. Alright? To have the probability, you need to multiply the probability density with the range. In this case, the range is dr. Another example, the probability density of a speed in the x direction is proportional to this. This is from chemical kinetics, the kinetic theory of gas. So if you have gas particles moving around, the probability density is proportional to this, e to the power of negative kinetic energy over kBt. And we're focusing on the x direction. All right. So there are 2 examples about continuous probability distribution. And in that case, we need to visualize the probability density. Okay, we cannot visualize probability. Now here's some discussion about the probability itself. The probability of finding the electron in the hydrogen atom at any radius is just exactly 0, because you need a range to get a non-zero probability. Alright, if you have a range from R1 and R2, let's say from 0.8 angstrom to 0.9 angstrom, and then you can integrate the probability density and you get a finite value, which is the probability for finding this electron within a spherical shell between the radius 0.8 angstrom and 0.9 angstrom. So you can do that. What if you have a range from 0 to infinity? Of course it's going to be 1. That means the probability of finding an electron in the entire space. Actually, when you see this, that means the entire universe. Well, it's just 100%. The probability density of speed in the x direction can be normalized. This is not normalized. It can be normalized. If you integrate this from 0 to infinity to be 1, I mean, it can be normalized. You just need to evaluate this integral. We have this n as the normalization factor. Alright, you just ensure over here, the total probability of finding the particle with a speed between 0 and infinity is 1. So you just need to do that. Alright, over here is just a graph of this probability density. Alright, for the electron in the hydrogen atom, it's just this. It looks like this. The probability density of speed in the x direction is proportional to this, and we can normalize it. We just need to set it to 1. If you know how to integrate this function, you will see n is the square root of 2m over pi kbt. We do this kind of derivation in chemical kinetics. The normalized probability density is just this, the normalization factor times the exponential function of negative kinetic energy over kbt. What about velocity? The normalized probability density of velocity is actually 1/2 of this. You can see when this is divided by 2, this 2 disappears on top from the top, appears on the bottom, because I just divided this normalization factor by 2. Because the velocity is sine. So if you have a speed of 1 meter per second, the velocity can be negative 1 meter per second and positive 1 meter per second. They share the same speed, so I need to divide this by 2. And on top, I should have this negative m velocity squared over 2 kbt. But it turns out this squared is the same as the speed squared. Alright? Because negative 1 squared is also 1. The probability density distribution of the one-dimensional velocity is a Gaussian function. Okay, for velocity, it's going to be a Gaussian function, bell shape. It looks like this. And if you integrate the normalized probability density for velocity, so if you do this from negative infinity to positive infinity, you'll get 100%. The physical meaning is simple. The probability of finding a gas particle moving at a speed between negative infinity and positive infinity in the x direction should be 100%. Just please note the difference between speed and velocity.